Good morning, everyone. So shall we start now? Because it's
Yes, ma'am. Please.
yes, yeah, yeah. So good morning, everyone. I hope you are enjoying all the sessions. Today we have two sessions in morning. Bhavani sir will be taking. In afternoon we have another session of HEC HMS at 3 p.m. So I just have a general suggestion. Whenever you attend this one, before that you try to install the software and come so that you can also do it along with the resource person, right? Okay. So coming back to the session, I'm very happy to introduce Dr. Bhavani. He is also the coordinator of this particular training program. And he is very active in all the programs whatever he organized. So just very happy to introduce you, Dr. Bhavani. He is an assistant professor in the Department of Civil Engineering in our same department itself, and specialized in hydraulics and water resources. He did his PhD from NIT Rourkela, and his PhD work has contributed to the UKERI project. It is a project collaborated with the UK, Indian government, and with UK. On non-uniform flow modeling in compound channels. He has authored in many international papers, international journals, and the good part is he also attends a national and international conference. And the good part of this is attending is you can have a collaboration with those institutes, foreign universities, and in national universities. So that is a good part of attending conference, and you can also collaborate with the other researchers working in the similar areas, right? And his work has been presented internationally, like the conferences that is organized at St. Louis University, USA, then IRSTEA in Lyon, then in Egypt, another conference in Egypt, and also recently he attended the River Flow Conference organized by Liverpool Moore University in London. And he is also a reviewer of many international journals, and he is an editorial board member of Scientific Reports Journal, which is a Q1 journal, and he is a co-PI of the MMTC TTC funded project Capacity Building for Design and Entrepreneurship, and he is an active member of NIT Patna Incubation Center, and he also chaired many sessions in international conferences like Hydro 2020 and Riverflow 2024, and delivered many invited talks at different universities and also the national workshops. He is an active member of professional bodies like IAHR, ISH, and also recipient of Engineer Nanda Nandan Das Award in the year 2024. I'm very happy to introduce you. Over to you, sir. So you can start the presentation. He is apt person for this presentation. Okay.
Thank you very much, ma'am, for the brief introduction. So now we'll start the session. So the screen is visible to all of you?
Yes, sir.
Yes, I think
Okay.
everybody can hear you.
Okay. So very good morning to all participants. So we are on the day 2, and this is the first session. So the topic for the present session is numerical modeling of dam break flow using open flow. Okay. So here the numerical modeling. Okay, so numerical modeling. So what are the different techniques we have in water resource engineering? What are the different techniques? First one, we understand about the experimental things, experimental modeling. In second place, we can write the numerical modeling. And in third place, now in last 20 years, we have the AI models. Okay. And if you can see the experimental model, okay, from you can see this from 16th century from Newton. After that, Archimedes. Before that, Archimedes. After that, Euler, Bernoulli. They have the eminent researchers who are on the domain of fluid mechanics, hydraulics in experimental modeling. With evolution of computers in 1940, 1950s, during the Second World War, you can see the numerical modeling comes into picture. We have the equations like Navier-Stokes equations, Saint-Van equation, which are the differential equations. To solve those equations, we need manual solving those equations. It is difficult. With the help of computers, we can do the numerical modeling task. And in present days, from last 20, 30 years, AI models comes into picture, starting with the artificial neural network. Now we are moving towards deep neural network, cloud computing, quantum computing. These are the advanced techniques. So you can see the evolution of modeling technique from experiments towards the AI model, quantum model. You are moving towards in this direction. And from 1950s and still numerical modeling is very important tool, because AI model is a data driven model. If you give the good data, you will get the good results. If you give the poor data, you will get poor results. Garbage in, garbage out. Okay. So it depends upon your data sets, AI models. So till now, scientists, researchers are working on the AI models for efficient use in the domain of fluid mechanics, hydraulics. In climate change, AI models are giving um, accurate results, somehow 70%, 80% accurate results. But till now, we are not fully rely on the AI models. And from the past, you can see the experiments is always a benchmark for a water resource engineer. If you are performing the experiment and in physical experiment or field experiment in the laboratory experiment, you can see the, you can validate the physical process in the lab and you can replicate the prototype in the field. So experiment is always a good approach. AI model is a future approach. What is going on numerical models? Mainly whatever the software we are using, because this is a hands-on training session. And in this hands-on training session, we are mostly focuses on the software. Okay, how you can perform some analysis of hydrologic and hydraulic using software. But in our each session, our focus is to what is the background of that software. How it is very simple. A 10 class student or intermediate student can use a software and get the result. Okay. And if you give him proper directions, he can also explain some things. But the background, what is the reason? Why that software giving this much of value? Why there is a 15% error, 20% error? Why this is giving 5% error? Which different methods why it is giving? That is very important. And numerical methods for all software, numerical modeling is very important. Yesterday, we have session in second of Dr. Kamalini, where in which session Madam discussed about the CA software, Conveyance Estimation System. The background of that software is numerical models. That is the Navier-Stokes equations. Okay. So in that model, Madam discussed some philosophy of that equations. Okay. If you understand the numerical model, then only you can develop some softwares. Otherwise, as an end user, only you have to use some software blindly and getting our results of the day-to-day problems. Okay, so numerical modeling is very important concept. Everyone, every water resource engineers should have some knowledge of that. If it is your not the main research area, main domain, still you should know some knowledge of numerical model so that you can understand the background of any software. Okay. Next thing is dam break. Okay. So in dam break analysis, I'm already, the term is dam break. That means there is a breach inside dam. Then why we're analyzing this? If there is already a breach, why we're analyzing this? Because before 1980s in India, many dams are constructed without any dam breach analysis. Dam breach analysis is helping us if anything happened to the dam, what are the chances, what are the devastation, catastrophic effect happen to the human life and the property of the society. So if you can analyze the each dam of the country, then if in case of mishappenings, we can take some safety precaution, take some measures. Okay, there are many issues to prevent the dam break. After dam break, what are the measures that can be taken? We will study that thing only after dam break. How much area will be inundated? Okay, if you know the inundated area or how much time it will take the flood from the dam break to reach to the downstream side, how the evacuation plan can be executed, which type of construction towards the downstream of the dam should be made, that can be planned after dam break. Before dam break analysis, before dam break, what type of foundation, construction material, those are not part of this today's talk. Okay, so dam break occurs due to piping or overtopping. These are the two main reasons because of which dam break generally occurs, and many other reasons are there, like the slope failure, shear failure, okay, poor construction material. So we are not focusing on the construction aspect. We are focusing on if dam breach happens, how much area will be inundated. That is the focus. And now I'm introducing a term that is a open source code, that is open form. I hope many of you have heard this term. So if you heard the water resource engineers, the research scholar and experts, if you had the term open form, you can say yes in the chat box or give a thumbs up in the chat box. If the open form from the today's session, if you are not listening from me for the first time, so you can see earlier you have acquainted with the term open form. Give a yes in the chat box. If you all are already heard about the open form. If this is the first time, okay. Renu, I have a response from Renu. Other participant, please respond. Okay. Ram Abhishek, yes. Harinder Gupta, Hari Prasad, no. Okay. Dr. Prem Kumar, no. Okay. Rahul, yes. Rahul is our students. Okay. So open form for many of you are new. So I can say that there is a 50-50% in our audience, those who have heard about the open form. This is an open source tool. This is an open source tool where we can perform some numerical modeling. Open form is a extension of C++ package freely available. In this open form, the open stands for the open source. It is freely available, and form, the full form is field operation and manipulation. Okay, so our field operation, not only for the water resource engineer, many other in domain like structure, geotechnical field, they are also using this thing. Okay, and manipulation means you can model without, you can manipulate the model, you can trial and error process, you can see what is happening in the what in the model. Okay, you can change the boundary condition. So there is a freedom of changing in the software, in the open source. In the laboratory condition, if you are performing some dam break problem, okay, you are constructing a dam in the laboratory, and now after the dam break, one set of experiment, you need second set of experiment. So to maintain a second set, it is require a lot of cost. But when in the numerical model, that is the interesting part, is many times you can do the model without paying a huge cost. So you can try hit and trial different models, different conditions to get your best results, get your optimum results. So open form, if you learn this thing, you can generate your code, you can generate your user defined problem. Not only dam break analysis, you can go with the flood routing, river confluence, sedimentation problem, scouring problem, many other problem you can define. You can write the code from themselves. And in today's scenario, in advanced AIs, you can use the chat GPT, DeepSeek. 10 years ago, we don't have the codes, don't have the access for a civil engineer, water resource engineer. But 2025, we have the lot of access. If there is errors in the code, you can find the error, you can ask in the DeepSeek or chat GPT, you will get the code and you can run the simulations. So it is very user friendly. Initial period, it will take some time, and this 1 hour or 1.5 hour session, this is give just a ignition to your research domain, to your thoughts, to or those faculty members present here, they can explore this software with your students. They can learn a new dimension in the hydraulics engineering, and they can write their own code and solve some hydraulics problem. So I have shared yesterday the installation guide. It is freely available in the website. After the end of this session, I will share all these materials with you and the link through which you can get the all tutorials. Today we are explaining a tutorial of dam break analysis, and initially looking into the different equations. Numerical modeling means differential equations, Navier-Stokes equations. Many of water resource engineer fear of those equations. Convection, advection, diffusion. When you had these terms, always we try to move away from these equations. If you are using, if you are learning the concept slowly, gradually, you can have fond of this equation, and many difficult problem can be handled with it. Okay, so I hope you can understand the numerical modeling. This is the medium of experimental and AI. This is the mid of the modeling techniques. Then the dam break process. Mainly after the dam break, what will happen to the downstream side? That is the objective. And open form. This is the open source software for field operation and manipulation. We can try, we can write the code, we can simulate the results, and we can, if the results are not up to mark, we can again reframe the boundary condition, initial condition, again we got our problem solved. So some points, some dam break simulation, you can find it from the Google's or from research paper. What are the importance, catastrophic potential, safety point of view, emergency planning, and through dam break analysis for a particular dam, we can recommend some simulation tools, some models, some definitive equations through which those problem can be handled. These are we can set some benchmark for different dam break process. So these are the importance of dam break simulations. You can see in the present last 5 years, you can see in open form is publications are there in the good Q1 journal. In the main purpose of the research is to publish a good research paper. Okay, so open form is, if you can do any research in the open form, this is now very likely to be accepted by the good journals. In a journal of eco hydraulics, ocean engineering, pure and applied geophysics, and several journals in the last 5 years, you can see many water resource related problem can be solved using open form. Okay, from the USA, Germany, Netherlands, and some are from the Middle East, they are also working there. But from India, very few IITs, NIT, or state universities, private universities are working in this domain. Mostly, it can be seen the water resource engineers, the researchers working towards a software model or in a laboratory condition experiment. If there is a funding, you can do the experiment. If no funding, then what? We need lot of data sets. If from the literature, we can get the data set and we can do the data driven model, AI models. But those models, AI models, are the background is, you can say, the hollow model, garbage in, garbage out. A computer scientist develop those models for their problem. We are blindly implementing to our domain, like training, testing, those things we are doing. There is the accuracy. In near future, we will get robust model. Till now, the researchers, hydraulic engineer, trying to find it out how much accurate, whether we can implement those things in real time situation or not. In future, I am very optimistic about that. AI, deep learning, quantum will supersede the experimental work and the numerical work. Nevertheless, this numerical model and experimental model will give its position, its important role in to the researchers and hydraulic engineers. So my intention in this session is to move towards a new concept, that is numerical modeling, and by writing codes, your own codes. If you can write your own codes, we can develop our own softwares. Many of the times we are dependent upon various software, like yesterday the software is CS. It is developed by University of Birmingham by Siono. In 2018, Siono visited NIT Patna during Hydro 2018 conference. In his PhD work 1989, he has developed that Siononite method and implement in CS software. Okay, and in the afternoon session or next session, we are studying about the HEC, RAS. This HECRAS is developed at US Army Corps by USA. Then we have like Mike, maybe from Netherlands or European country. Mike is there. The background of development from Netherlands or Germany, Mike has developed from those country. But from India, very few hydraulics or water resource software are there. So it is a time we are saying that we are moving towards the Viksit Bharat 2047. And if you are dependent on the software only, then are not understanding the background of the software on the numerical models and utilizing the ready-made, ready-use software at the as an end product and simulating and solving our problem up in Indian context, will not be the Viksit Bharat. So our students, our teachers, faculty members, researchers, my request you to all to go through the background of the software, write your own code, and try to build. If you are solving some problem like flood routing, dam break, write your own code. And through collaboration, we can develop our own indigenous software. If you are in a private university or central government university, you can approach. If you solve your problem writing a code, then that code can be commercialized. That code can be make into a software. But because it is little bit a higher level, using a software by clicking in different icon or looking into a tutorial, it is very easy to use a software. If someone is there to demonstrate you the software, it is very easy. Generally, Hacker's training program is going on, my training program is going on, ANSYS Fluent training program is going on. They are there to sell their product or to sell their concept. If not product, if freely available software, that means they are selling their concept, that they are developing something, you are using that thing. But now the time has come, we the Indians, the researchers, we should develop our own codes. And without understanding the numerical models, open source codes, we can do these things. So everyone to think towards this open form or any related software. Now coming to our problem, that is dam break flow. So here I have given a problem statement. So you can see in a dam break problem, generally if you have observed or somewhere you have heard about the dam break problem, there is a dam, there is a bridge, then in the downstream area, there are some very colorful diagram, inundation is occurring at the downstream area, some water surface plot are there, stage discharge curve are there. Those are in HECRAS, you can see that is 1D models, but in open form, you can do 2D and 3D both. But here in this open form, what we are doing, we are taking a very simple concept. Like in open form or in numerical model, generally we have to close the domain. We have to define the domain. If you do not define the domain, then the equations cannot be solved. So we are defining the domain in boundary we are giving, and we have to solve the equations in this domain only. Then we will get result at different point inside the domain. What are the result? In a dam break flow, the results are the water depth, the water velocity, the discharge, post dam bridge, what is happening to this velocity, this depth. So if we disintegrates the domain into several cells, several nodes and elements, you can see the several. I am discretized the domain into multiple rectangular and square type of grid. And now if you want to solve the differential equations in this grid, we will get the value in these locations, in these nodes. For different space and different time, what is the value of depth of flow, discharge of flow, we can get in this nodes only. So for the simple use of open form, we have consider a very simple example, tutorial example, that is a dam break is occurring in a closed condition. We can extend for real-time application, we can extend the scenario in a real-time scenario, but for understanding the concept, how the equations how the boundary condition, how the initial condition are playing role to capture the surface. When there is a dam break, how much flood wave will be generate? So how much flood wave will be generated? So if we consider a big structure, it is difficult to understand. Therefore, for the present case, we have defined the problem like a rectangular plume of length 584 meter, 0.584 meter height. So this is a 0.584. This is square plume. This is not rectangular. This is a square type plume. This is a square. And at time t0, what will be the water column height? This is the water column height. That means there is a dam in existence. We can think this as a dam, and there is a water column of this much height, 0.292, and the width of this water column is 0.146. If the dam breaks, that means the water will, this in the right hand side of this water column will break, and there is an obstruction we have considered with a very minimal dimension 0.048, and the width of this obstruction is 0.024. These are nothing but a replication of some downstream obstruction. Mainly in the downstream, we have the trees, we have the buildings, we have the industry in the downstream side. So this is replicating that scenario. You can see the dimension is very small. Why we are considering a very small dimension? Because in open form, we are making the domain into various number of grids, and in each grid there are several nodes. Okay, several nodes, and we will calculate the value at each node. If you take very high dimension, okay, so there will be lot of nodes, lot of elements will be there. So the cost here in numerical modeling is the time. In experiment modeling, the real cost is our money. But in numerical modeling, the time is very important. To execute the problem, whether the equation is or boundary condition is actually giving us the good result, to know that how much quickly we are finding the result, whether this boundary condition is correct or not. So that is the important. Time is important here. If you are increasing the size of this boundary condition, then there will be lot of nodes, lot of elements will be there. So the computational time will take a longer durations. Just like if you have heard about the ANSYS Fluent, okay, that is also a numerical modeling tool software, and OpenFOAM is a open source software or open source tool. And if you increase the dimension, then the solution take a longer durations. Therefore, we are considering a very small dimension. And you can see the 0.024, 0.048, 0.584, 0.292 in this tutorial. I'll share the whole manual PDF is available in the OpenFOAM website. I'll share those tutorials after the class, and each code is written there. And with me, my resource scholar, Mr. Sasank Sekhar Sandile, is with me. He will give you the demonstration after the theory discussions in next 10 to 15 minutes. So in that tutorial, you can see this small value they have considered. The reason is, as a tutorial, we need to find the end result, the simulation result, what is happening, how the dam breach is there, after hitting the obstruction, how the surface wave will be generated. To visualize those things. Unless we visualize something, we cannot believe whether it is working or not, whether we are able to capture the change in the surface wave. Okay, so whether how we are interlinking with there are two phases. air and water. So when the air phase and water phase both are to handle, we have to go with the multi-phase analysis. And we have to consider the atmospheric pressure. And from last 15-20 years, it is a challenge to handle those type of problem in two-phase systems. Different approaches are there, like Lagrangian approach. That approach basically tracking the surface. And Eulerian approach is there. Eulerian approach, this approach will not track, it will capture the surface. So generally Lagrangian approach means we have to track a particular fluid particle, how it is moving, upwards, downwards, in lateral directions. We have to capture, and it is difficult to track if there is no mesh inside the air part. Generally, when you develop a mesh, we generally develop the mesh only in domain of interest, but tracking the surface is little difficult than capturing the surface. For capturing the surface here, volume of fluid approach is there. Okay, so volume of fluid approach, there are some factor like alpha. We'll discuss it in next slides. Okay, so we'll follow the capturing surface approach for solving this dam break problem. And this smaller value, the reason is that the quicker will be the solutions. And you can see this is the 2 times 0.024, 0.4048 the 2 times, and 0.292 it is the 8 times, and 0.146 is the 4 times, and you can see 292 into 2584, this is the 16 times of 0.024. So the grid will be generated with a multiplication of 2, 2, 4, 8 in this manner. In yesterday class, you have developed a cross section for a compound channel by giving the coordinates in CS software. Similarly here, to define this domain, this obstruction, we have to define the geometry, define the coordinates in the similar manner. Okay, so the problem is here, it is clear. This is a dam, and just the problem is this is a dam. What will happen if this right hand side will fall, and if it will interact with this obstruction, then if it will hit the boundary, then how it will comes back? That is the whole problem we need to find out. And here the approach will be used volume of fluid approach. In volume of fluid approach, volume of fluid. So in this approach, we'll see the how much volume is occupied by the fluid, whether it is air or water. Okay. Then this is a 2D explanations, two-dimensional, u and v component of velocity or u and w component of velocity. It can be extended to both the direction. And here the multi-phase, because more than one phase, two-phase system we are considering. And we need to consider the viscosity, density, and surface tension. Because when a surface is occurring after a dam break, so it will interact with the air and the water, the surface will interact with the both the thing. So you have to consider the change in the viscosity of the fluid, if it is for water or for air, how we are density of water and air, viscosity, dynamic viscosity of water and air, surface tension sigma of water and air, how they are related in this volume of fluid approach. We need to look into it. And also you need to define a gravity vector, because this is an open channel flow scenario. Dam break analysis, it is not a pipe flow case. So gravity has an important role in the downward direction, how to give a gravity vector. And dam break analysis is an unsteady flow case. With time, we can see the variation in the discharge, variation in the depth, variation in the water surface profile. So this is an unsteady flow case scenario. And the simulation tool is used is the open form. It is very important, free and customizable. And these are the flexible solver are there, different solver. Interform is one of the solver which will be used now for dam break analysis for solving two-phase flow like air and water. And you can do the parallel simulation, high performance simulations. And to display the result, you need ParaView is a visualization tool through which you can see the results like discharge, shear, depth, depth of flow. We can see it through the ParaView. So now going to the different solver of open form, there are different solver: ecoform, simple form, pisoform, and interform. And different solver are different purpose. These solver are ready-made, inbuilt in the open form. These are the package available. Just like in MATLAB, if you are doing in Python, you can do the NN package, M5 NNPSO. Those are the packages are available embedded in the tool itself. So for solving the hydraulics problem in open form, various packages already are there. You no need to write the Navier-Stokes equation by yourselves. You no need to write the turbulence equations. You just need to call the interform. The code is there already. And if you want to change something, you can do it by yourselves. You can modify some constants, some coefficients. You can do it by yourselves. So this is user defined, and you can simply call the interform package, and in interform we can solve incompressible flow problem, immiscible fluid phase, where the two fluid are not mixing with each other. There are two different surfaces for air and water. They will not be mixed at the surface. And we can, through interform, through this surface capturing methods, we can find out the sharp interface. Okay. And the methodology behind that is finite volume method. So in numerical modeling, very popular method in Western countries, they are using finite difference method, volume method, and finite element method. In 1980s, in IITs, these methods have come into picture around 1995. Many researchers in 2000, many NIT, IIT researchers side in 1980s, the faculty members are doing their research, and it is taking a 20 years time to reach to the India, the researchers. to work on these domains. Already many lectures are published in this domain. Similarly, in open form, in last 7 to 8 years, okay, this is from 1980s, and India, this is popular in 2000. Finite element method, finite volume method, finite difference method, okay, and many NITs also, the master's program, they don't have this concept also, this numerical modeling course also. So open form, this is very new. New one, 8 to 10 years. So we need to focus on this in open form modeling so that we can be stay ahead from different other. So in this, the finite volume method and PISO is there, which is a pressure implicit with splitting of operator. Okay, several lectures are there. This PISO, understanding the PISO BHOP method, this will take independent minimum 2-3 lectures. But the purpose is here to just the background. So VO, volume of fluid, PISO is a pressure implicit method. This is a non-iterative method. Non-iterative method means step by step we will not get the value of pressure or velocity while solving the Navier-Stokes equations. We will get a coupled equations and it will directly give the pressure and velocity at a particular node, not by a iteration manner. And it is also using to capture the surface Moore's technique for interface. Moore's is a multi-dimensional universal limiter explicit solutions. This is a technique developed in 2002. I think the research paper is there. This technique is adopted in open form to capture the interface. And we can use different form models, but the results from different solver, you will not get the good surface capture. So the interform is the best suitable solver for a dam break problem. So in volume of fluid, 2 or more immiscible fluid, immiscible means they don't mix like water and air. The core principle is phase fraction, that is alpha. This is nothing but the volume inside a cell upon total volume. If we can discretize the domain into several cells, you can see these are some cells I am drawing here. This is one cell, this is one cell. If the water surface is like this, you can see this surface is filled with air. Okay, so the volume inside the cell is how much for air. We are considering it as 0 if there is no water. If partly filled, you can see here this is partly filled. So suppose this is a 40% filled, the volume, this will be upon the total water like 100, that is the value is 0.4. To capture the surface, we need the phase fraction, that is alpha. Okay, so you can see the then the volume of the cell, individual cell, you have to calculate the alpha value. Here the value is will be in a range of alpha 0.7. Here will be range already we have calculated 0.4. Depending upon the volume emptied or volume filled by water upon total volume of water. Because our main problem in hydraulics is we are considering the water as a denominator, the full volume. Okay, so here you can see it is written alpha equal to 1, cell is full of fluid. Full of fluid means for our present case, we are focusing on the water. But if you are the same scenario, if you are doing some aerodynamics analysis or study of some turbojet engines or rockets, space, then the fluid become their air. So your alpha will be 1 for the fluid one, that will be air for that case. But our case, we are focusing on the water surface. Our problem, the capital V is the volume filled with water, not the air. And VI is the volume, the portion of that cell filled with the water. Okay. And 0 to 1, see, 0 means those cells are empty. Okay. So capturing in a domain, in a closed domain. So if there is a wave is generated, so capturing those surface, we need this intersection, interspace cell. No need to find out the value of alpha in this domain, or no need to find the value of alpha in the empty domain. We need to find out the value of this intersection domain. Okay. So depending on the alpha value, you can say whether there the surface, the wave is generating or not, or there is a trough, there is a crest in the wave. So 0 to 1 in between, if alpha value is there, there is a presence of a interface. Volume of fraction is generally utilized here for the recognizing the interface. Okay. So VOF along with the Navier-Stokes equations, you can see the momentum equation in X, Y, Z directions. These are the convective term. These are the shear term. These are the pressure term, and the surface force and gravity force. Convective term, basically convection. Basically, it means the fluid is flowing. Water is flowing, that can be handled by a convection equation, first order differential equations. Advection means this is a subset of convection. Fluid is moving along with some sediments. Then that will be considered as an advection equation. Some extra term will introduce in that convective equations for that sediments, or you can say in a pollutant transport problem, the pollutant in a airflow, that is a advection problem. And there is another term you used to hear in equation, that is diffusion. This is nothing but a diffusion form. The shear stress, the eddy viscosity, these are the diffusion. Diffusion means the mixing of this pollutant with the fluids. How the mixing is occurring. This is generally denoted by the second order equations. So first order equation are the generally convective, space-wise manner in the first order. Advection, if there are some pollutants, some sediments are there. And the diffusion means the mixing process. And convection and advection both are a fast process, because there is no mixing. They are just traveling from one space to other space, one position to other position. That is the convection and advection. So those are faster. But in the mixing diffusion process, it takes times, longer durations. Okay. So the eddy viscosity, the turbulence, those are the mixing thing. In the viscosity, if you see the turbulence, this is the air and water will entrap and they will travel or circular motion, helical motion. They are giving a vortices like pattern. So that will be handled by this viscosity, eddy viscosity term, diffusion term. So those are the physics behind Navier-Stokes equations. Along with the continuity equations, that is conservation of mass principle, continuity equations. And in the surface, because there are two surface, water and air, we need to see the surface tension value. It is handled in interform software. The sigma, there is some coefficient value, interface curvature value, and the change in the volume fraction alpha. alpha value may be changing from 0.4 to 0.9, 0.95, depending on the volume of fluid inside that cell. Accordingly, the force, surface tension force will change, and the whole thing, continuity equations, surface tension force, momentum equations, and the change in the viscosity and density, because inside a cell, the water and air is changing interchangeably occurring. So the value of rho and mu inside a cell at the surface is changing. So that changes how we can handle in this linear manner. We can handle those changes. So alpha, that fraction of rho one stands for the bottom fluid, that is for our case is the water, and rho two is a air for the second phase. So this total alpha is 1. So alpha 1 minus alpha. So this is the mathematics linear equation utilized to assign the value of density and viscosity inside the cell of interface, not for this rho value. Okay, not for this value. Here the value of rho is fixed, that is density of water 1000, or what for air, whatever the density, 1 gram, density of water 840, density of air, the default value will be there, but at the interface the density and viscosity value will be changed in each cell, and that will be handled by these equations. So altogether, this 1, 2, 3 and the momentum equation 4 coupled together to solve the Dambreck problem. And the volume fraction equations, how the volume fraction will be handled. This is a convective equations. Divergence of alpha u generally means delta x, the change in velocity in delta y direction and delta z direction. How the alpha is still changing in all three directions. If you are considering 2D, then only in x and y direction, what will be change in alpha and velocity value. Okay. So volume fraction can be handled with this convective equations. And here you are giving the initial condition and boundary condition. Boundary condition is defining the domain boundary, that rectangular problem isolated from the outside environment. So all the governing equations will obey inside this boundary only. And initial condition, that means time 0. When there is no dam break, how the scenario, how the cells are there, what is the velocity value in each cell, what is the depth of flow, that is time 0 value. We have to, in time dependent problem, you have to give the initial condition in the beginning of the simulation. Otherwise, simulation will not occur. In 1D flow, in HECRAS also, you are giving some initial condition, boundary condition. Otherwise, you cannot initiate the problem if you are not defining the domain. You will not get the results at each node. So these are some difference in initial condition and boundary condition. Actually, we have taken around 45 minutes. Okay, so these are the alpha value for water volume fractions. Initial condition, the fixed value is considered as 1. Cells are 100% water. These are the value. Okay, we are considering in this Dambreck tutorial. Okay, these are the default value already available in the Dambreck package, but we can change according to our demand. Okay, so these are the some boundary condition value. But how will define this boundary? Okay, this square shape boundary, how we can define this thing? What will be the left side boundary? What will be the right side boundary? Where there will be no slip condition. No slip condition means the relative velocity is 0. The relative velocity 0 means the velocity of the fluid particle attached to the boundary require that velocity, that of boundary. That means boundary, if it is static, the velocity of fluid at the boundary becomes static. That means zero velocity. Those are the conditions we have to consider. And if the boundary is moving, like a sedimentation problem, that is the sediments, bed sediments, then we should not use the no slip condition. Okay, so we need to identify the further, you need to define whether you want a no slip condition or a slip condition you are requiring. Then about the kinetic pressure, zero gradient. Okay, del U upon del X. Initial for the bottom left wall and right wall, the gradient is zero. That means change in velocity at the wall is zero. Wall is this is zero. That means in the wall is fixed. Whatever the value is assigning at the wall, in the each node, the value will be same. The change, there is no change in the boundary. Okay, and uniform value is zero is assigned for the atmospheric pressure, because we are considering atmospheric pressure as zero for this present problem. So these are some different boundary conditions: left wall, right wall, lower wall, atmospheric pressure, and the default phases. So those are given as empty. Okay, and the descriptions are mentioned here. These are some references. You can go through these links. I'll provide this PPT to you all. You can go through these softwares, and these are some references I have considered for this making this presentation. And now I request our research scholar Sasank. Through him also I am learning the open form. It is not like that, yeah, I knew everything. And we are everyone want to learn new concepts. Through my PhD students, I'm learning this new open form software from last 1.5 years. We're together, we are doing work with open form. And now I request our research scholar Sasank to demonstrate the dam break tutorial in next 30 minutes. And if you have any questions, you can put in the chat box. And during the tutorial stage, if you have any doubt, you can raise your hand and we can take your questions at that time. So Sasank, you can now share your screen.
Thank you, sir. I think it is audible to everyone and my screen is visible to everyone.
Yes, yes, your screen is visible.
Okay. So yesterday we have shared a installation guide in which if you go through, you find that we require three things for simulation using OpenFOAM. The first, Ubuntu. Ubuntu is required for execution of the codes, and other is OpenFOAM software. It is inbuilt into the Ubuntu. And other is ParaView, which is required for post-processing of the software. So we have, in my system, it has been already installed. So when I open the Ubuntu, it is visible. There are lots of folders, which are by default present there. So we only want to go through this folder OPT. So if in this folder there is OpenFOAM is already there. 6 means version is 6. And there is also ParaView. So in OpenFOAM, we have gone through this. We go to the section of tutorial folder. In this tutorial, there are various tutorials are there related to various problems like combustion problem, compressible problems, financial, heat transfer, incompressible, and multi-phase. So in this tutorial, we are focusing on our multi-phase case, dam break case, which is a multi-phase problem. So when we go through the multi-phase problem folder, we have lots of solvers are there. But in this tutorial, we consider interform solver for the study. So we go through this interform solver. In this, there are lots of problems for laminar problem, LES problem, RAS problem. RAS is basically we have turbulence models in which like K omega, K epsilon models are there. In these RAS models, LES is a sophisticated turbulence model which requires lots of time for performance. And there is laminar, there are lots of problems are also there. So we choose laminar flow for this tutorial because it takes less time, so that we will demonstrate in this tutorial within a limited time. So in this we have find dam break. So in dam break folder we have three subfolders are there, like zero, constant and system folder. Every open form tutorial or case has these three folders. So zero folder is there for defining our boundary condition. Constant folder is there to define fluid property and turbulence properties. And we have also system folder is there for meshing, simulation control, defining our solution schemes, solvers, etc. And here is also all run folder is there. So if I open this folder, they are given some commands. So these are basic commands which required to be executed in Ubuntu so that we run our applications. Okay. So if I want to run this tutorial, so what I need to do is to copy that case. I copy this case and come back to OPT folder. Here back. Here. At original from where we have started in Ubuntu. So tutorial is present where in OPT folder. So now we come to our home folder where I have created my username and created my dictionaries from where I want to run my simulations and store that there. So from home to when I come to my directories, go to open form. In run folder, I have created. So I have pasted the tutorial case here. So it is come into my home directory. Okay. For running this, what I will do, I will open Ubuntu. I have already installed that. So I open this Ubuntu folder. So first of all, it is required to source the open form in this environment. So for this, what we will do, we will use a command to source this. So this is the command to source our open form. Actually 6 represent our version. If you have other versions, you may write open form 7, 8, 9 or whatever. So when we press enter, so we are under the open form environment. So if you want to list all the directories which are present inside this folder, so for that we will type ls. ls means list directives. So we got there 4 directives are there. So we have, if you see, I have keep my dam break case in the open form folder. So I have to go through the open form. So for that I have to change my directives. For that I have to write cd. cd means change directive. And I have to go to open form. For that I have to press only capital O and tab button. It get automatically open form, or we can also write it simply open form. So in that, I want to check what are the directives are inside this open form folders. For that, I have to execute once again ls command. ls means list directives. So it has this folder. So I will change my directives again by pressing cd space tab. Again, I have to see what are there. So I have run directory, and I again list all the folders are there. So we have to run our case dam break. So then again we will change our directives to dam break.
Pause. Actually, what Sasang is doing here, actually just already dam break simulation package is there. is calling those Daembreak package to solver so that it can simulate the result. So this is the so that command.
Written there. These are the
These are the
steps.
steps.
These
These
codes
codes are the step to calling a package to for in your system for the run of the program. Okay, so you can see here the ls for the list, cd for change of directory. Okay, change of directory means from a main directory it is coming to your directory to your system. Okay, now
Again, we will list our directives, all the directives present inside the Daembreak folder. So we will see there are three. I have already stated that there are typical structure of this open form. We have three folders: zero folder, constant folder, and system folder. And all run and all run. All run is the file which tell us how to execute the command. So I have already opened all run. The first application we have run is to the block mesh. It has been given here. So I copy this. And for pasting that in Ubuntu, I have to just right click. Okay. And this will, when I press enter, it will create a mesh. Okay. This mesh consists of 5 blocks. It is starting from 0. This is a typical C++ convention. 0 block, one first block, second block, third block, fourth block. And it creates a bounding box of from 0002 0.584, 0.584, 0.0146. Yes, sir. No, sir. Actually, this is a domain, whole domain. And we have created some patch names: left, right, lower, atmosphere, and default places. We will show that. So if I want to view this, for that I have to call paraview. For that I have to write touch command for creating a file named any name like test1, and its extension should be .4. So it will create a file name as test1 which has extension of form which will be readable by paraview for viewing our result. So I have created that touch file. We will see at the last by executing all the commands given in all run file. So I have run the application, block mesh, and created mesh. Then second application is to run set field. So again, I come to my Ubuntu terminal and then press right. So it will create a set field. Okay, set field is basically the water column we have selected initially before the breaking of dam. So this is the box in which water is present before the break at t equal to 0, which is our initial condition. Set field allow us to define initial condition of water column in this range, which is if we see that this is exact same as this dimension. The height is 0.292 and width is 0.146. Here it is extending from 0 to 0.146 in x direction. In y it is 0 to 0.292, which is height, and in z direction it doesn't matter because we haven't made calculation in the z direction, or also our domain is not up to that extent. In -1 to 1, if domain is not there, there is no calculation is happen. We will take any value of this z coordinates. Okay, then the last command given in our all run file is the dollar applications. We know that we have used the interform solver. So for running this, we just require to type interform. So our simulation has started. It takes few minutes. It has completed. It has been completed. So if you want to see our results, we will go to that folder. See, initially we have only 3 folders: zero, constant, and system. Now we have lots of folders created at 0.1, 0.2, 0.34, like this. These are created while running simulation, and values has been stored at every interval listed here. So we have this form extension which we have created. So this file contains all our results, which we can open in the para view. So here, if you apply that, we get this condition. So if here these are the fields: U, alpha, P, P rho, G, H. The field we have defined in constant folder are only U, alpha dot water, and P rho, G, H. So these fields are present here. So if you see alpha water, how it changes. So actually at 0 it is not available. So it is at 0.005. 0.05. So here red color shows that the legends, we may change it, legend from 0 to 1. Okay. The red color shows that it is water. Blue color shows that it is air everywhere initially. And here there is from red to blue color is there, which shows that there are both phases are present in these cells. To accurately capture that, we'll see. These cells have full of airs because it is blue in color. Exactly reds are full of water. But here are some cells which has not blue, not red colors are there. It means that here both phases are present. So in this tutorial, we want to capture this interface between air and water. So as we move, see how this is our reservoir. When dam breaks, how it moves and travel through and hit that obstacle, and how the water surface has changing. So we will see by moving it. By going to next frame. So we will able to see how our water surface interacts and its surface changes. We may also see that how velocity is changing. We may also draw streamlines, velocity vectors to analyze more about this. Suppose I am using the vectors. It will show that how it formed the vertices and how the velocity magnitude changes from place to place at different time intervals. Okay, this is the simple test. I just run it. Now we will show that how it has been worked, how the mesh has been created, how the geometry has been formed from the start.
So this is our end result, but what exactly you have to do? Okay, package is there. If you use this syntax, you can do the simulations, but without learning the geometry condition, what exactly Sasang has done just before doing this Dambek package, what he has done. Now
he will
he will
demonstrate
demonstrate those things. How
he
he has given the coordinates for geometry, how he has given the mesh, how he has set the field condition, boundary conditions. Then only you can simulate using the open form tools, and you can learn for other problem also, not only dam break, in other pipe flow case, compound channel flow case, river confluence case, you can make your own domain. The concepts remain the same, like geometry formation, meshing, boundary condition, and set of fields. Those are the same process you have to follow for different applications in hydraulics. So, Sasank?
So initially we have seen that there are three folders. I have also explained that zero folder is for defining our fields. So our fields are alpha water, P rho GH, and U. In constant, we have G folder, which define the gravity. These are transport property and turbulence property. We will see at last. In the system folder, we have the block mesh, which is required for creation of the geometry. So if I go inside this, so we have lots of vertices are there, boxes are there. So how will create this? I want to explain this. No. Hope both side of the screen is visible to everyone. Yeah. So here, if you see in the left side of the screen, some vertices are given, and right side we have our problem domain. So first of all, what we will do in this to solve this problem, we have to create rectangular boxes or blocks so that we will mesh our domain. So for that, we have made these blocks. Second block. So this is our block 1, block 0. Actually, it is starting from 0, block 0, block 1, block 2, block 3, and block 4. So here are given some coordinates. So it is starting from this point. So this is coordinate 1. This is coordinate 2. This is coordinate 3. This is coordinate 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So this is the two-dimensional, but open form understand 3D. So what we will do, we just created a bit dimension is z direction. But what we will do, we want mesh it. So what happens? The calculation is not occurring in that direction. So if open form doesn't understand 2D cases, so it understands only 3D. So what we will do in every 2D problem, we just define there is a z direction, but we want mesh in z direction. But for defining our geometry, we need require these dimensions. So our geometry is like this. Something like this. So now the vertices, which is in backside, suppose this is the front and the back side, it is starting from 30. I have I write that coordinates with different color. So now it is 13. It is backside of 1, phase 1. This is our vertices. The vertices in the backside is 13, name 30. This is named as 14, 15, 16, like that, 17, 18, 20, 21, 22, 23. Okay. Actually, I have started from 1, but we have to start from 0. It will be 23. Actually, I have to start from 0, but we have started from 1. So the one vertices is 0, 0, 0. The another one is it is located at the point given in the problem 29. It is 0.292. So here, if you see this, we have used a conversion factor of 0.146. If you multiply 0.292 by 0.146, it comes out to be 2. If you multiply 0.292 with, sorry, divide. If we divide this by 0.148, we get 2. So 2 is the coordinate of this point. Second, what is this? Here. Third is here, which is 0.2168 if you multiply by that factor. Or otherwise, we may also write this by converting the convert to meter or this factor to 1. We may also write it start from 0. The first vertices is 0, 0, 0. The others are 0.092, 0.09200. We may also write it like this. 0.29200. The other one should be 0.292 plus 0.24. Plus 0.2. Is 0.292 plus 0.024. It comes up to be 0.316. 0.3. The next is 4, which is 0.584. 0.584. We change this to 1. We are not taking any conversion factor.
So what Sasan done earlier in this problem, the problem is defined by open form software. Okay, so they have given a convert to meter factor as 0.146. Okay, therefore, in the vertices, in the first coordinate, they are putting 0, 2, 4, 6, 8 in this manner. But if you are considering the convert
as 1, so you have to give your real
to meter as
coordinates.
1 to give your real coordinates. Just like in
previous day,
yesterday you are doing in
CES,
you are giving the coordinates, the exact coordinates. You have to give the exact coordinates here.
To locate
To locate the obstruction, to locate the each vertices, you give the exact coordinates. But
here, if you are
here,
giving the
if you are giving the convert factor,
the
like
point
the
146,
146,
you can give the whole
the
number.
whole number.
Okay, this is
This
nothing but a
a
normalized
normalized
case. If you are
case. If you are
giving
giving
a
a
convert factor,
that means you are normalizing the coordinates
of
of
0.146
0.146 domain. Otherwise, you have to give all coordinates. So this is the way
to give
define the whole domain. Okay, in X, Y, Z direction,
Each
each block you have to mention in this manner. Now you go to mesh. Okay. So in this manner, you can do for the all 21.
Okay.
Because we don't have time, already 12:05.
So in this manner, we will define all the vertices.
All the vertices of the block.
We have created 5 blocks. 5 blocks. So we have created 5 blocks. For that, we have blocks shape is hexahedral. All the blocks are hexahedral. So here we have starting from 0. Actually, we have to start from 0 only. So here is the 0, 1, 2, 3, 4. This is 4, 5, 6, 7, 8, 9, 10, 11. This is different color. This is 12. This is in the back side of 0 vertices. This is 13, 14, 15, 16, this is 16, 17, 18, 19, 21, 20, 21, 22, and this is 23. Actually, always we have to start from 0. Otherwise, we have to change all these. If I'm not starting from 0, we have to here 0 from 1, 2, 3. These are basically hexahedral. Suppose I am taking block 0. So it has been created with 8 vertices, which are 0, 1, 5, 4 from front side. And if you take the back side, 12, 13, 17, 16. That's why it has been written here. For block 1 to create, if we use these 8 coordinates to define a hexahedral block, for 0 block, it should be like 0, 1, 5, 4. And again 12, 13, 17, 16. It should be in anti-clockwise direction. It is a convention we are using. Okay. For suppose this is our block 1. For creating this block, what we need to define the how the vertices should be defined: 2, 3, 7, 6, 14, 15, 19, and 18. So it has been written here that 2, 3, 7, 6, and 14, same 14, 15, 19, 18. So like this, we defined all our blocks which we want to mesh. We don't want to mesh this area. If you mesh this area, so what happens? Flow is occurs through that domain. So no obstruction is working there. So what we did that we don't mesh this area to act it as a obstacle. Otherwise, if we mesh this area, and here we will use, if we use 6th block or 5th block and use these coordinates like 1, 2, 6, 5 and 13, 14, 18, 17, etc. So what happens? This domain is also meshed or discretized, and flow is happen through this area. So, but we want this as obstacle. So we want mesh this area. So like this, we defined our hex blocks, and here 23, 8 and 1 are the message or number of messages we wanted to create in X, Y, and Z direction. Here 23 means we want 23 number of times, number of messages in X direction, 8 in Y direction, and 1 in Z direction. I have told we are performing a 2D simulation case. For that, we assign a certain value in the Z direction, but we want mesh in the Z direction, so that no calculation will occur in that direction, and our case will be two-dimensional. So this is how for block, this is block 0, this is block 1, we have 19, 8 and 1 blocks in X, Y, and Z direction, blocks discretize or meshes in X, Y, and Z direction. Here simple grading 1, 1, 1 meaning if I have using 1, that means all 23 spacings or meshes in X direction are equally spaced. All are uniform. If I use 2 here, that means expansion is there. So it is not uniformly distributed. It is expanded from initial to last. Then we define we don't have edges, we define boundaries like left wall. To define our left wall, we required 4 vertices to define a patch like this. This for block 0, this is our left wall. So to define this, what we required? 0, 1, 4, and 12. Or we like that, we may also write 0, 12, 4, and 1. Like this, for this area, our block 2, this face, we define with the 4 vertices like 4, 16, 20, and 8. Likewise, we also define our right wall, lower wall, and atmosphere patches. And okay, so like this, we defined our boundaries. Suppose this is our left wall. So left wall is represented by these 2 patches here for block 1 and for this block 4, 16, 20, and 8. So while doing this, we will create this block mesh file. Again, I'm converting it so that I will run it again and show the results. So this is how block mesh works. It may be open in the same file. I will reload this file. So this is our mesh we have created. So we change, if you want to change anything in the mesh, we may change this area block. Suppose I want to mesh 23, more than 23 in X direction. So may I change this 30? Let's see it's work or not. Then I run again the block command. So it fails. It shows that inconsistent number of faces between block 0 and 2. So what happens? What happens? This is our 0 block. This is our second block. This is our second block. So in 0 and second, what happens here? If you see, this is our 0 block. This is our one, this is our second. I have changed the number of messages required in X direction from 20 to 23 to 30. But I haven't changed in block 2. So the faces of both are combined. So I have to change the block 2, the number of messages in X directions. Like if I have to change this, I have to change this also. Otherwise, mesh will not form. So I have changed both. Control save. And then once again I execute block mesh. Then see it will work. So we may find this, post this mesh. We may expand or compress this message where we require that with the help of this. Yes, sir. Yes, sir. If you want to see that, it is visible. I have reloaded. So this is for 23. Now it is 30. Now it is 30. It is for it is final. Sorry, more final. So we may also, if you want to more finer near the obstacle. If you want our mesh to be more finer near the obstacle, so what we will do, we will decrease it, compress our meshes in X direction. So anything I will do with block 0 in X direction, I have to mate also to block 2. Otherwise, mesh will not form because both are dependent. I save this. And if I run block mesh, we will see this is initially, and if I reload. So now our cells are compressed in this Z direction by a factor of 0.8 I have taken here. Not in others. Only block 0 and block 2.
See the fineness in the left-hand side and post mesh in the
Right.
You can see the
fine
fine mesh here in the left hand side and coarse mesh in the right hand side. Because Sasan has reduced the meshing size to 0.8 in block 0 and block 2.
Actually, not mesh size. I have compressed the blocks in the right direction. So here in left side, if you see, here the meshes are coarser. Now it is getting finer near this.
Finer near towards the
Obstruction. Because this is our block 0 and block 2. We have done it to only 0 and block 2. Others are as it is. So this is how we modify our mesh. We create our geometry. So best way is to find a problem identical to your problem and start with that and make modification in that case. So after meshing, we will have to go to the boundary conditions. We have defined boundary condition in that. So we have defined left wall, right wall, lower wall, and atmosphere. So we will define our boundary condition on all those patches that has been defined in the block mesh dig file. So here is the velocity boundary condition for velocity field. This is internal field uniform 0, 0. Initially velocity is 0 everywhere. And for boundary field, we have created patches, left wall, which shows no slip, right wall, it is a wall, there is no slip condition is there, no velocity is there, lower wall, still it is no velocity is there. For atmosphere, we use pressure inlet outlet velocity field, which is a derived velocity, derived boundary condition. And the other faces that are remaining, like front or back faces, which has been considered as default faces, which is empty. Because this boundary condition is used because we want our simulation to be in two dimensions. So we won't make any calculation in the Z direction. So that is why we have used the empty boundary condition.
Okay. See, here you can see, go to the previous the boundary conditions slide. Here you can see in the boundary condition, the no slip, it is written as no need to write the velocity is zero. In fluent or in any other boundary condition where you are imposing boundary condition, that time you have to give the velocity value as zero or at the boundary. So here the command is like no n small case, then slip s is capital. Like no slip, only in text form we can given and it will be executed as no slip condition. Okay, no need to write the velocity value, just like if you are using in other software like Flow 3D and Fluent, you have to give some value, no slip value. But here you can write simply this. These are the syntax. Empty is the syntax. So no slips is the syntax. Then pressure inlet outlet velocity. These are the syntax, right?
Yes, sir.
It is these syntax are the embedded in the open form software.
Sir, it is very flexible. We may also create our own boundary conditions and change according to our requirements. So for that we have to work little bit harder, and we may create our own boundary condition depending upon our problem. So it is quite possible to do it in open form because it is open source. So we may change the equations of the boundary condition which are not default here. Now we have other boundaries, P rho GH. So it is given for all the patches that has been defined already in the block mesh diff. So this zero folder is basically for defining our boundary condition. Here is our constant folder in which there is G folder in which we define acceleration. So here the value is minus 9.8. In minus 9.81 means in y direction, negative y direction. So it gravity force is acting in negative y direction. And here is the transport properties we have. For water, it is nu and rho value is there. For air, it is nu and rho value is there. And sigma, the coefficient for surface tension between air and water interface is given here. So here turbulence property is there. In this case, we have used laminar. So here laminar. Otherwise, we may use any turbulence model. We have to just write on and to define that turbulence model. In system folder, there are some also folder. This is set field. This is set field folder, which is default value, which is showing the default value, volume, a scalar field value, alpha dot water equal to 0. Means alpha dot water value should be 0 in the all on default value, it is default value everywhere, except the regions we have defined. So box to cell is a region where we have defined that alpha water value is 1. So before, sir, this is our case. We haven't executed set field command yet. So we haven't defined any set field. We have just mesh it, created mesh. So this is the value. Suppose I want to increase the height of this. Earlier we have seen that the height of the water column is 0.298. I have domain 0.5, more than 0.5. Suppose we have changed this. So now if we run set field, okay, it is already there. So we have to remove that. Previous files are already there. Actually, it has been already written there, so I have changed this because we have already executed this. So now while changing, Okay, actually we have changed the maze. So again we have to start from the face, remove all the messages. Actually the maze has been changed. So yeah, run it once again.
As Sasank changed the maze, therefore set field condition is also
need to be changed.
changed.
Otherwise,
Otherwise, you have to go back to the original maze, and then the set field condition, the same set field condition will be prevail.
So anyway, if we will remove this from here. We will go to tutorial case, and from there we will take once again the alpha dot water, and then once again come to our
So now only remaining other thing constant, only how the set field will affect, for because already Sasank have made some changes in the geometry and meshing, therefore some error occurs. So now we are going back to our original files, and we will change only in the set field, and we can see whether the set field is changing or not in the present model. So these are the old block mesh.
So now it works. So now the height of that it is from up to 0.5. We will see that also here. In previous we have seen that it is up to 0.29. Right? So actually, I mean, it will be there if I run the software. It is not showing at the 0 time. That's why. It is taking time. Actually, we have increased the number of meshes, so it takes larger time. We have increased the meshes in X direction from 23 to 30. So that's why this time it takes longer time. Now see, the water level has been increased. We have defined our set field from earlier cases from 0.29
or 292.
0.29 to 0.5. Now it is here. Now it's here. So like this, we made adjustments, and one more important control file is there. So decomposed file is there for decomposing our domain into different subsections, so that we will run them on parallel. Suppose I have a machine of 4 cores, so I want to distribute my load to all 4 cores. So what we will do, we divide our domain into 4 cases. So for that we will use decompose pardict file, and we subdivide our domains, and one core handle one domain. So
Okay. Do not discuss this. Actually, these are the tricks to how in your system you can simulate. You can. There are 4 system core in a CPU. So how you can use your CPU and to do the simulation process in a faster manner. Okay. So main purpose is to
learn
learn
this
thing and
simulation.
simulation.
It will
It will take for real-time simulation. It will take 2 days, 3 days, sometimes even 10 days in a 32 GB RAM system. And there are high performance computers, supercomputer are there. They will do that simulation in 1 day. Those are taking 5 to 6 days. They can be done in 1 day. So you have to in decompose. You can give different core of your CPU to task different manner. So your result will come very quickly. Okay. So they are the latter part, but important thing is very important thing in open form. You have to create the geometry, meshing, setting the boundary condition and set field, and then how you can visualize the output that through paraview. Okay, those skills are important, and during simulation this decomposing tool will be also be required. If you're in your laptop 8 GB RAM or 16 GB RAM to perform more accurately, you can decompose the things. Okay, thank you, Sasank.
This is also important. This file is control file.
Control file, another file is there. Sasank, just
So it takes 2 minutes, but sir, it is from here we set our simulation time, start time from 0 to end time, and we want our delta time, delta step T2 this, and we are writing our results at this 0.005. So we have, if you see our folders while run, where we have run, so these are the folders. Actually, we have written in control file that we want at interval of 0.5. So that's why these are all are listed here. Suppose in case our system power off, so we don't have to start from 0. So it is a benefit that suppose we are writing at 0.05 and it stops at 0.5. So in the second case, we don't have to go from 0. We will start from 0.5 and from up to whatever time we want. We have taken here one. We have taken here 1 second, one time step. We have for the easy or fast simulation. But others are default some values we will be giving it. So it is also flexibility that if in the other safety softwares like NCs, it is a problem that if simulation stops in between, so you have to start from the start. But it is flexibility here. We may store at whatever interval we want and starts from where it has been stopped.
Yes. So thank you, Sasank, for a wonderful demonstrations regarding the open form. I hope our participant get a brief knowledge or demonstration. It is difficult in 1 hour to learn those things unless you perform by yourselves. Okay. So any questions to all participants? Any questions, any doubts?
Sir, I have a doubt.
No question?
Hello, sir. Hello, sir.
How do you calculate the inundated area downstream in this model? Okay. So you have, see, if you run this thing in the downstream side, there will be different number of cells, and each cell you have the dimension. And in this particular problem, you can see we have defined the dimension up to 0.546, right? So in the downstream side, we have the length of 0.546. After the wall, if you can see in that PPT, the downstream side, after, are you able to see the screen? You can see here the downstream side from these to these positions. If you look into my cursor, this is the position. So this is the length. And if you can write a command, what is the, after from this position, how much volume of fluid fraction, how much cell is occupied with value 1. Okay, so that number of cell in longitudinal direction will give you the distance covered by the downstream manner. Okay. And here in the closed domain, for a shorter duration, shorter time frame, we have done the simulation. Therefore, a high column water reached the last downstream boundary. It is hitting the right side boundary. But if there is no boundary in the right hand side, it will go towards the downstream side. That means we are giving a big domain, big square or big control domain. Inside that, we have the access to identify the cell, fill with the water, and we can calculate those cells, how many cells having the value 1 that stands for water, and that is the distance covered from upstream to downstream. The major thing in this open form that whether we are able to do the simulations perfectly, and those equations and those interfaces, those wave generation, sometimes near the dam break at zero position towards the downstream, and 10 kilometer, 15 kilometer, 20 kilometer, the wave, the magnitude of discharge will be reduced towards the downstream side. So the value of that magnitude in the beginning of the downstream. So those things can be handled by 2D or 3D model more accurately as compared to the HECRAS model. HECRAS model is also a good model, 1D model, but in this open form, you can see the velocity in Y direction, what is happening, in Z direction, what is happening, what is the eddies formations, which type of structure can stand out in time of flood. Some building structure having some different type of design can withstand the flood in the downstream side, maybe 5 kilometers away from the dams. Maybe some other buildings will be collapsed, not because it is not designed in this manner to handle the flood wave. Okay. So inundated area mainly calculated by the number of cell having value 1.
Sir. Hello, sir.
Okay, Zita, I hope you got the answer.
Hello, sir.
Okay, so we don't have many questions. So in a near coming future, open form modeling, very few experts in India are working from IITs and NITs. We will do another physical mode or online mode only on physics-based modeling, open form modeling, FDP, if the participants demand them, and researchers, faculty members want to do that course, we will communicate further. So thank you everyone, for all the participants for attending this session. And this is not only give you a new perspective in research in hydraulics domain, and you can try this with your BTech students, master student, PhD students. If you are a faculty, if you are not a faculty, after your PhD, you can explore this domain. And definitely in next 5 to 8 years, our country will develop definitely some good softwares of our indigenous softwares. We are hopeful. Okay, thank you, everyone. So we have next session at 3 p.m. by the scientist from NIH. So Dr. Rosni will introduce the session at 3 p.m. Thank you, everyone. We'll meet around 2:55 p.m. in the afternoon. Thank you.